dropping knowledge.
Are we recording?
Yeah.
Okay, great. Hi, everybody. I'd like to introduce you today to Jeremy. He is he's all these things, but he's done more cool stuff than I think anybody I know. That's possibly true. So pay attention, and as always with any Blue Stamp speaker, you are encouraged to interrupt him and say, hey, but what about that, or hey, but what about that, or tell me more about that. He's going to give his talk, and you'll have a chance to ask him some questions, but don't be shy in between. So with that, I will pass it off to Jeremy.
Cool, thanks, Dave. Yeah, the purpose of this is just to give you enough context to be able to ask me intelligent questions. I don't really want to speak at you guys for a long period of time. I'd much rather talk to you and hear what you're working on and be able to help you in any way I can. So I'm just going to run through some of the stuff I do, some of the things I'm interested in, and we'll leave it at that. And yeah, interrupt me at any time. Raise your hand, call out, I don't care. Okay, so I like to start off by talking about curiosity now whenever I'm talking to especially younger people, and talking about how it's influenced me and how I assume it's influenced all of you to bring you to be in a program like Blue Stamp. I think the number one most important thing that's driven me to do anything I've done that's led me to success or just learning something interesting in my entire life has just been out of a desire to know more and be curious about the world around me. And I think that's what Blue Stamp's all about and why all of you are here. So I like showing this slide because when I was first thinking about how to talk about curiosity, I was like, I need to come up with some. When you're working on a presentation, people always tell you oh, you need to have some kind of real life example or some paradigm or some analogy. And I was like, oh, I actually met a robot. I'm a roboticist, and I met a robot called Curiosity. Okay, very easy lead in. This is a Curiosity rover, or a model of it. A lot of people. This picture also doesn't do it justice, but most people don't realize that this thing is the size of a minivan. It's extremely large. And so something that looks just like that is up on Mars right now. And a few years ago, I was at JPL, the NASA Jet Propulsion Lab. I was working on augmented reality stuff at Google, and they wanted to use some of the tech we were working on to facilitate their basically spaceship and rover building process. So that's my little blurb on Curiosity. And then I want to talk a little bit about struggling, especially because you guys are all in your second week right now, right, of Blue Stamp, and you're all probably struggling with all kinds of things that you don't understand and you don't know why they're not working yet. And part of what I want to tell you is that you're gonna leave in 10 weeks having learned a lot, but also still having no idea what's going on about a lot of stuff, and that's totally okay. And it's how I feel every day. Even as someone who does what you guys are doing professionally every day, I leave every day having learned something new, but also having 100 more questions for every one question that I answered. So I want to impress upon you that that's normal, and to not let it dissuade you from doing the work that you guys are doing on your projects. Again, analogies, right? This is a learning robot that I worked on a couple years ago that tries to teach itself to walk using machine learning algorithms and sensory input. You basically say, get from point A to point B. It struggles and flops around. It doesn't know what it looks like or how its motors are configured, and then it just flops around and evolves its own gait until it learns how to walk, much like you guys will do. There'll be a lot of flopping around for the first couple weeks. Okay, and then I want to talk about how I first got into engineering. So this is 10 years ago. You guys, I don't know, have any of you used Lego Mindstorms? Yeah? Have any of you used this really old version of it? Does this look familiar? Probably not anymore. I can't imagine. Okay, yeah. So this was my first foray into, you can loosely call this engineering. I wanted to make a prosthetic hand. So I started off with the only thing that I knew how to use at the time, which was Legos, and I made this thing, which is frankly terrifying to watch. But that progressed over time. I worked with some researchers. Was I talking to you about instrumentation amplifiers? This was my first experience with instrumentation amplifiers. using myoelectrodes to detect electrical muscle impulses in my arm and use that to control a prosthetic arm. So it works for me, but it would also work for someone who doesn't have a hand, for example. Yeah, at the end of it, I had built this cast that I was wearing on my arm, but could also be kind of cut off here and equipped on amputees to control a prosthesis non-invasively. This is kind of where it ended up. So that's me using the muscle signals in my arm to control a secondary robotic arm. And I know it looks really crappy and stuff, but that's where I got started. And it was after I did that first project, I knew I wanted to keep doing this kind of stuff forever. This was I just found this very recently. It's the earliest example I could find of something that vaguely resembles an electrical schematic. Yeah, I just think it's funny to look at because it's so bad. That's it. Okay, so now I'll talk to you about some of the more interesting research and projects and stuff I've done. This is a project called Machine Metabolism. This is what we call a self-assembling robotic system. This is aimed as a technology to be used in truss structures like cell phone towers, but also in truss structures in space, like the International Space Station, where you want to deploy a swarm of robots to reconfigure a structure autonomously. So this is a robot that can grab onto specialized truss structures, disconnect them, reassemble them, reattach them. This is just a short snippet, but it can also reattach them and move them around the structure. And so you can imagine this is just a simple square structure, but you can imagine something with thousands of trusses with hundreds of robots all going around and repairing things and building things and taking things apart. This was my first foray into robotics, really. I don't know if you consider the prosthetic thing robotics. And then this was a couple years ago now, 5 years ago, but I still do a lot of work with audiovisual stuff, music, lights, sounds, dancing, whatever. I don't do the dancing because I'm exceptionally bad at it. I'm also exceptionally bad at the music composition, but I know people who are good at it, and so I lean on them, and then I do the effects stuff. This is from a performance I did several years ago where she had these Wi-Fi connected LED glow sticks that I could control the lighting on, and then there's another one of my friends back there synthesizing music on the fly, and then I'm wearing a glove that's synthesizing music as well. Dave mentioned this briefly before, getting into like not college research projects, but other stuff that I've done. How many of you have used a 3D printer? Wow, I actually expected more than that now. I'm sure you all will have in some capacity by the end of the summer, whether sending stuff out or using it yourself. Okay, how many of you know what a 3D printer is? Okay, yeah. So, when I first taught at Blum 4 years ago, or the summer before that, the first summer that Blum existed, and I came in to guest talk when I was working at MakerBot, and I asked like, who knows what a 3D printer is? It was like 50%. So that's like not that long ago. So this is one of those technologies that's kind of come into existence in the last couple years that I feel privileged to have worked on and designed electronics for. I designed the electronics for this one. And so I've been involved in that space for several years, the fabrication space. I think it's fascinating to be able to build things on demand. I also think that 3D printers have a lot of limits, and that people put a lot of expectations on what that industry would become unfairly, that I agree with. And so part of what I'll talk about in a minute is new methods of fabrication and other things that I'm working on. Also spent a couple, this video doesn't portray it super well, but spent a couple of years, or actually my master's thesis, so I went to school at Cornell, undergrad and master's, and my master's thesis was on LED lighting and building lighting systems that could emulate sunlight, both not just in terms of the color that we perceive from the sun, but the entire spectral distribution. So if you look up at the sun at any given time, it looks white-ish, sometimes more blue, sometimes more red, but it's white-ish, and that's because it's a composition of every visible color wavelength. and the distribution of those shifts over the course of the day, which changes the hue from redder to bluer. But I did a bunch of work with social scientists who are studying how the color of light impacts our circadian rhythm and our biological clock, and makes us sleepy and things like that. And one of the more interesting outcomes from that research, and this has been proven over the course of many years now, is that blue light suppresses melatonin production. Melatonin is what helps you sleep. So how many of you have heard that you're like not supposed to look at a screen or use your devices right before you go to bed? Okay, do you know like why that is? Other than the fact that your parents just want you to go to sleep? So the reason for that is the technology that's used for the backlighting in those is a blue wavelength based technology for the most part. And you have photoreceptors in your eyes that respond to blue wavelengths of light and suppress melatonin production. And we evolved that way because the sun in the middle of the day is predominantly blue wavelengths of light. And so we want to stay awake in the middle of the day. That's how humans evolved. We're not nocturnal. So you can, by exposing yourself to blue light late at night, it suppresses the melatonin again like it's supposed to in the middle of the day, except now it prevents you from going to sleep. So I did a bunch of research into developing lighting systems that didn't do that and helped accommodate to help you sleep better. I stopped working on that when I left to go to Google. Some other people continued it as a business. The business did not succeed, and I'm happy to talk about that. Although I wasn't involved in it when that happened. Yeah. And then another major part of my life is doing stuff like this and talking to people and helping people. And these are some students with a book that I wrote a few years ago that I'm long overdue to write a second edition on, but I have no idea when I'll find time to do that. But basically, I had made a lot of videos and tutorials and stuff online. There's dozens of projects that I'm not going to list in this presentation that I've made that people wanted to duplicate or learn from, and I wanted to share that with people. And people repeatedly asked me for a book to help them learn these things because they learn best that way. Ironically, I never read instructional books when I'm trying to learn something new, but other people seem to, so I was happy to do it. And the book did really well, and people still use it as a textbook. It's used as a textbook in the class where I first learned to use an Arduino in college, which I think is hilarious. So I spend a lot of time doing talks like this, helping people on the internet as much as I can. It takes a lot of time, but I enjoy it, and I think there's a lot of curiosity out there. You guys are all curious, and if you don't nurture that or give people an outlet to do something with it, then it goes away, and I think that's awful. So I'm here to do anything I can to help people nurture that. That brings me to the last 3-ish years of my life, up until this past October, where I worked at Google X, which is Google's research lab development thing, for lack of a better way to describe it. I was there, my official title there was hardware astronaut, and that was because I worked on building hardware that was aimed at helping Google accomplish its moonshot goals. So that's what Google calls, Google branding speak for their crazy bets that will cost them an enormous amount of money and have a relatively low chance of fleshing out into something useful, but if they do, they have the potential to be really amazing. So it's high risk, high reward. I spent my time there as a system architect and electrical engineer. I designed the electronics inside Google Glass. The main reason I did that and was excited to work on that project is the applications for products like Google Glass and Enterprise. I have a couple pairs of them and I use them when I go hiking and stuff to take pictures, but I don't really think it's an important use of the technology. I think an important use of things like that and things that people are still working on is heads-up displays for things like medical applications, handicapped people, things like that. So that is now how glass is used. There was certainly a failed attempt to make it a consumer product. Again, happy to talk about that with you guys if you want. I have many opinions on it. But I'm thankful that while I was there, I was predominantly working on building the enterprise version of Glass. So it's not one that you've seen, or unfortunately probably anyone who's not working on one of those enterprises will ever actually see or use, but it is out there. There's tens of thousands of them out there being used by various enterprises to do things in healthcare and things like that. And I did the electronics design for the inside of that. And that was when I had the opportunity to go visit JPL and work with a bunch of other partners who wanted to use Glass to do interesting things that weren't feasible with any other form of computing. So I spent 3 years doing that. Most importantly, learning about a lot of supply chain, hardware manufacturing, how you bring a hardware product to market. I went through all the pain and struggles of those things, learned a lot, learned how ridiculously small it's possible to make something. And that's in part why I'm now thankful to be doing some of the other things I'm working on, which are very different challenges. This is Jarvis. This is just a quick picture of it, but Jarvis stands for Jeremy's Astute Residential Virtual Intelligence System, also known as an excuse for me to call it Jarvis. Hold on. So this was in the Wall Street Journal a couple weeks ago. I'll play it. But this has been my side project. My side project for the last 3 years. I don't know if you can hear that at all. I told him to introduce himself. Now he's speaking. You're probably not going to be able to hear it at all, but I'll voice over it. Jarvis is speaking right now. It's a distributed home automation platform that's natural language voice controlled. So like you're working on with Amazon Echo over there, similar idea, but all the hardware is built from scratch by me. It controls my lights and my music and my window shades and my alarm clock and a bunch of screens around my home. All kinds of stuff. There's not really anything you can get. And okay. Yeah. So that's a side project that I've been working on for a while now, and I'm happy to talk in more detail about that. A lot of people ask me why I didn't leave Google to pursue that as a company. To pursue home automation stuff, because the platform's quite good. It works quite well. I use it in my daily life every day. The alarm clock wakes me up in the morning. It brings on the lights slowly over the course of 10 minutes. It plays me the latest news clips. It opens the blinds. It turns the lights off and plays some music and helps get me out of bed and all these fun things. But I think it's important to have hobbies that are separate from your day job, and I really enjoyed doing the home automation stuff as a hobby that is a really nerdy way for me to de-stress at the end of the day or on a weekend when I just want to work on something without product requirements or making it accessible or multilingual or making it manufacturable or any of these things. And so it's just a fun thing for me that I like working on the side. And I'm in the process of moving again, so I now have to set it up again. This video is actually old. That never worked, but I fixed it and made one that does work now. Actually, I do have a video of it. One second. I'm quite proud of the way I got the shades to work. So these are how the shades are set up now. You can do everything through your phone or through a voice interface, but I just pressed a button on my phone. And there's a big motor over there that spins a wheel. I'm using a particle photon to connect it to the network. And it pulls the shades open. And that was mechanically very challenging thing. So I'm not a mechanical engineer, and this proved to require a lot more torque than I thought it would. And the right way to do it is with the right gear ratio and the right mechanical design, the right pulleys, but I have no idea what I'm doing, so I just put in a ridiculously high torque motor. And that's okay. why I don't want it to be a product. I just want it to be a fun thing that I work on. Okay, so last thing. So this is what I do now, and you guys already heard from Brendan earlier this week, right? Yes? Yeah? Okay, yeah, so Brendan's my intern this summer at Shaper. Shaper's a startup. I left Google in October to join Shaper to lead electrical engineering there. Shaper's composed of me and 3 other people from my previous team at Google. So me, the industrial designer, the CEO, and the head of mechanical engineering all previously did those roles on Google Glass at Google. And the rest of the team is from the MIT Media Lab. And basically, we're making smart power tools. How much did Brendan describe this earlier in the week, or did he just talk about drones?
Told us about making a gear with it.
Making a gear with it?
Some basic rundown.
Okay, you got the basic rundown. So yeah, I mean, it's an augmented reality fabrication tool. Makes it like stupidly easy to make extremely professional looking products out of wood, carbon fiber, metal, plastic, whatever, with a tool that's portable and cheap. It doesn't require you to have a CNC mill that's the size of an entire room or costs $10,000. So that's what we're working on now. We're going to start selling that at the end of this summer. And I'm responsible for designing all the electronics in it and basically making it manufacturable. So that's what we're doing now. Also happy to answer more questions about that if it's unclear. But basically, it's autocorrect for your hands. You say you want to make something, you do the coarse movements, the tool does the fine movements for you, you get a machine quality output from a hand tool. All right, one more thing. This is a common question, so I'm just heading it off now because someone will ask it, which is like, what do you do every day? And the short answer is I have no idea. Every day is like totally different. But if I had to try to break it up, this is roughly how it breaks up. Right now, so it's a startup. And this list, I gave a similar list last year while I was still working at Google, and this list has changed a bunch. Because when you're working at a startup, everyone has to do a little bit of everything, which I love, and that's part of the reason why I'm there. So 15% of my time is doing like totally not technical work. Marketing, writing copy, working on our website, replying to comments on Instagram and Facebook and stuff. Getting ready to like do our launch, which is happening later this summer. 25% of my time is still design work, doing hardcore electrical engineering, whether it's math or schematic design or board layout or whatever. The difference here is that at Google I had a support team of I led that for the product that I was working on, but I had a support team of like 15 people to do aspects of it. Now I have to do all of it, and it takes a tremendous amount of time. And it's super interesting, and I love doing it, but it's also a lot of work. 50% documenting and analyzing design issues, implementing fixes. This is basically like when I make a prototype, I get something back, nothing ever works the way you think it's going to. I'm sure I've all experienced this in your first week. You put something together, you're convinced it's going to work a particular way, it doesn't, and then you spend the rest of the afternoon like punching yourself because you can't figure out what's happening. And then you eventually figure out what's happening, and 90% of the time it is something stupid. That's 15% of my time roughly. But that feeling when you finally get it makes it all worth it. Most of the time. Sometimes I just need to go home and fall asleep afterwards. Another quarter of my time is basically working with all my peers. So this is something I didn't stress enough earlier, but a big part of being an engineer, a big part of being a good engineer is working well with people who have different backgrounds and disciplines to your own. And so for me that means working really closely with mechanical engineers, software engineers, the marketing people, CEO, everything, and not just listening to them, but understanding them and being willing to understand things from someone else's perspective, especially when they have very differing opinions from you on how something should happen. This is particularly true with industrial designers and engineers. We butt heads a lot. It's like just the nature of the work. The industrial engineer wants it to be svelte with no cables coming out of it and no openings for airflow, and it should be, you know, half the size of what's possible and be able to fly. And then the reality, the engineering reality, is usually something quite removed from that. But as long as you can understand where the designer is coming from and understand the reason for their opinions, you can usually work together to get a middle ground that you're both happy with. Whereas if you just argue with them, you end up getting nowhere and you end up with a product that's considerably worse for it. And then there's 20% time doing lab bench work, so this is a lot of what you guys are doing this summer: soldering, hooking things up to power supplies, looking at an oscilloscope, testing things out. And then like just building stuff. Like we make a super awesome power tool. I try to spend at least one day a week in the shop. Like we have a shop and then we have office space in the same building. I try to spend roughly one day a week like just building awesome stuff with the tool. So this past week, that was a quadcopter. My brother flies quadcopters, and we want to test out cutting carbon fiber with it. So I got some carbon fiber stock. I cut out a quadcopter body. My brother came in, attached a bunch of electronics to it. We flew it around. And then out of wood, I made a sweet, like, I wish I brought pictures of it or something, but an awesome landing base for the quadcopter to land on. Painted it up, looks super cool. I'm moving apartments this week, and I intend to, first thing I need to build is a shoe rack. Yeah, and actually for almost all my electronics works, I build fixtures with Shaper. So when I get a board back that I'm prototyping and I want to assemble parts onto it, I build a holder that's the perfect shape with Shaper. Pop my board in, lay down my solder paste, and attach components to it. So I spend a good chunk of my time using the tool, and that's important because we're making a completely new category of product, and we need to see what works and what doesn't work and what breaks, and it breaks a lot. And so by the time it comes to consumers, it won't break a lot. It'll hopefully break never, because we'll have tested the crap out of it. We've already been testing prototypes of it for the last year, and we'll continue to test it for the next many months before it ends up in consumers' hands, so that we make sure that it actually works the way people expect it to. And yes, this adds to more than 100%. That was intentional. Okay, I have unsolicited advice to give you, but I kind of just want to stop there, and we'll talk about it anyway. It'll come out anyway, so I don't need to say it in the slides. But yeah, I'll stop there. That's it. I'd rather just talk to you guys now. Sorry that took so long. Cool? Good?
Who's got questions?
Can we like circle? I'm not gonna stand in front of the room. We circle up. Yeah. Yeah, how do we teach the robot how to walk? Sure. So that was called, the way we were doing it is called an assisted evolutionary algorithm. Basically the way it works is we give it a set of constraints and a goal, but try to define the constraints as loosely as possible. So in the case of that robot, we told it that it had 8 motors, two on each of its 4 legs, and told it how to move its motors to an arbitrary position, but not how the limbs were attached to each other or a kinematic model of its body. Then we say we use a tracking system or a sensor system to indicate its position and set its goal. So in our case, we put a little infrared LED on it, and we have a camera system overhead, and we say the infrared LED starts at position 0, and we want you to get to position 10 as quickly as possible, which was 5 feet away or whatever. So then using that information, you have the robot develop what we call fitness functions. So it'll basically try out a bunch of stuff and see how good of a job it does of getting towards fulfilling that goal. So its goal is to get from point A to point B as fast as possible. So the first thing it does is it takes its 8 motors and flails them randomly. It flails them randomly one way, and then it flails them randomly a slightly different way, with one motor getting preference or another motor not getting preference or something. Tries that 100 different ways. And of those 100 different ways, one of them, by pure chance, this is how evolution works, really, but by pure chance, one of those mutations, in the slight different way it moved its motor, caused it to move towards point B slightly faster than the other ones. Or whereas a lot of the other ones probably made it walk in the totally wrong direction even. So then it takes that one, and it makes 100 slight modifications to that one. And one of them inevitably does a little bit better. And then it makes 100 slight modifications to that one, and it does a little bit better. And then a few minutes or a few hours later, it's basically taught itself how to walk without necessarily having a kinematic model of itself by pure trial and error and assessing which of its best guesses for how to flail randomly gets it to point B as fast as possible. That's how it works. Yeah? No. The reason for that is we intentionally gave it an awful kinematic design. So in the particular case of that robot, part of the hypothesis was we wanted to start off with a kinematic model that would never exist in nature because we didn't want humans to be able to intuitively figure out a gait for it. So whereas a dog, for example, or any four-legged animal, like has 2 legs that go forward and 2 legs that go back, this particular robot had 4 legs, each perpendicular to each other, which makes no sense. They could only move up and down. They couldn't move back and forth. So like if you think about a square with a leg on each side of it that can only move up and down, and the front two can only move up and down, it makes no sense. But because it made no sense, there wasn't any way for us to guess what a good gait would be for it because it's not something that exists in nature. So that was intentional. So by the end, it did walk, but not what you would consider a traditional gait. It was more like a flopping bounce thing. But then what was cool about that is we could also chop one of its legs off, and it would teach itself how